Okay. All right, let's try this again. Okay. They can read the first part. All right. So a simple expression that incorporates both of these ideas is given by, and this is our differential equation. So this is now, if we are kind of comparing what we did yesterday to what we did today, or what we're going to do today. Yesterday, our differential equation was this. All right. And this said that our population, again, is changing over time at a rate that is proportional to that population. So if you look at this, let me actually erase this. It's kind of nice we have this. If I got rid of this expression here, isn't that the same thing we then did yesterday? Okay? So that's kind of taking this initial assumption into account that if our population is small, we can grow exponentially. So that's exponential growth with that. So if we now add this, here's why this still allows this number 1 to be valid with this model here. If your population is small, so let's say our carrying capacity, let's say the forest preserves down the Grange could sustain maybe 1,000 deer, and there's enough food and space, whatever, for them to live. If there is only 10 deer out there, if our population is small compared to our carrying capacity, then wouldn't, well, let's do this first. What kind of a number would P over K give you if the population is small relative to your carrying capacity? Yeah, it'd be close to 0, right? It's a small number. So again, I'll throw some numbers here. I can easily erase it with here, which is kind of the nice thing. So let's say we throw 10 deer out in the forest preserve, and it can sustain 1,000. Isn't that a pretty small number? So if I now do 1 minus, this is basically 0.1, all right? 1 minus 0.1 is really small. So wouldn't overall this parentheses have a value really, really close to 1 overall? So that if I multiply what we did yesterday by a 1, that's going to be largely what we did yesterday. It's going to start out growing exponentially. So that allows us to grow exponentially initially. Okay? So that's this first bullet point. Notice if your population is small compared to your carrying capacity, then P over K is close to 0. So the change in population over change in time is going to largely look like what we did yesterday, just KP, because the parentheses ultimately give you something close to a 1. All right? All right, so that's the first thing. Second bullet point. If our population starts to approach our carrying capacity, so focus on this equation right here now. If the population starts to approach the carrying capacity, then overall this fraction is going to start to behave like what number?
1.
The fraction is going to behave like a 1. And then overall, everything inside of the parentheses, then if I have 1 minus 1, that should start to behave like what? A 0. So if our population starts to approach our carrying capacity, then the change in our population starts to level off towards 0. Okay? Okay, got that? All right, third bullet point then, and what this is saying and why this differential equation satisfies these two conditions up here. If your population lies between 0 and K, so if this number right here lies between 0 and K, then the right-hand side of that equation is going to be positive, giving you a population that is growing. Okay? Fourth one, though, is saying if your population ever does exceed the carrying capacity, which is possible, the deer could eventually get out to like 1,100, but if our population, so now let's say the deer population is 1,100, but our carrying capacity is 1,000, wouldn't 1 minus 1,100 over 1,000 now give you a negative number? So that would now take into account that our population is bigger than carrying capacity. The right side is the negative, meaning our population now has to decrease towards whatever it can support. Okay? Okay, got all that? All right, so now, this is the big one. So there's going to be 3 things you're going to want to walk out of here and have memorized and sort of understand where this all comes from. So we do want to kind of understand these bullet points. But that thing you're going to want to know pretty well. All right, so now on the next page, it says a slope field is shown for the logistic differential equation. Oh, let's go back here. Let me not rush too much. Understand what all these variables now are. This big K is your carrying capacity. The P here and the P here, just like it was yesterday, that is your population. And then the little k, so you're going to have 2 different k's. K is still your percent, your rate. All right? So on the next page then, we took one of those, and I made a differential equation out of it, and we graphed it. So we did a little slope field. Again, here is the general form from the front page. This is what we did yesterday. It starts exponentially, but if we then take into account the whole, we're probably going to not grow exponentially forever. Uh-oh. Make this a little smaller so you can see that. So there you go. I went ahead and gave it some values. So I said little k is 0.08, so that's where this comes from. And then we said our carrying capacity is going to be 1,000. And when we did that, we create this differential equation here. Okay? And then this is the slope field for it. All right, so if we look at that slope field, it says, what happens when we start to approach a population of 1,000? So if we come over here to that population of 1,000, look at what happens as we go to the 1,000 there. Because that is your carrying capacity, that differential equation ensures that if we approach the carrying capacity, what happens to our slope, which is that field, dp dt should start to, let's put an arrow, should start to approach what? 0. Okay, and again, that's the whole premise of this, is that if we approach our carrying capacity, the population has to start to level off towards a growth rate of 0. All right, if our population was greater than 1,000, so let's say there were eventually 1,200, remember how we would connect those dots, sort of, just connect it? If I started at 1,000, wouldn't this one kind of feed into this guy right here? So if I am greater than 0, and we look at all these tick marks, what happens to P as we're greater than 0? I'm going to make this a little bigger so I can fit it in here. Underneath that, our change in population over time is going to be doing what? Or what's happening to our population will start to what? Yeah, decrease. So we're going to write this as my change in population, the rate of change should be negative. All right, that's our slope. Again, you're looking at the tick marks. Tick marks are your slope. Oh, hold on. I have that backwards. I need to slow my roll. Sorry, change that. This is less than 1,000. If we're down here, any of these, notice how all these will level off towards that. So if we are less than 1,000, then our slope, our rate of change, should be greater than 0. Our population can grow. But if we are ever greater than 1,000, so now if we're up here, if we're ever greater than 1,000, you should now see the slope of all of those are less than 0. Okay, we have a negative rate of change. All right, and then the last thing. Now you're actually going to kind of do what I was doing here. Plot this point, if you remember when I had you do these. So plot the point 0, 100. So this would tell us that if the initial population was 100 people, 100 whatever, deer, whatever we're talking about, sketch in the slope field that would go through this point. All right, and again, you're just connecting dots. This one probably goes to this guy somewhat well. But then we should see that these start to tend up. So I'm going to have this guy kind of start to tend upwards. I'm going to go to this one. To me, this one goes up here fairly well. But then as we get closer, don't all of these tick marks, like they should, start to level off towards the slope of 0. Okay? And then also keep this in mind now. Remember what exponential growth looks like. We obviously won't have a negative population, but doesn't the exponential curve start here? And what we said on the front page is this population might start growing exponentially. So doesn't this sort of start to look like the exponential curve? Remember, the exponential curve then kind of continues on this way. That's what we did yesterday. But what this model is saying, we're not going to continue to grow exponentially. Eventually, we're going to turn as we have more and more people, and we're going to level off towards our carrying capacity. Okay? All right. Now do 0, 400. So 0, 400 kind of looks like this. Now that this is a little bit closer to your carrying capacity, this is not going to be exponential for hardly at all, because we're going to turn pretty quickly and start to level off towards your carrying capacity right away. All right. And then the last one, if you go to 1,300, 1,300 is here. Now our population, when we sketch this, immediately goes in which direction? Yeah, down towards it, because we're going to decrease towards that carrying capacity. So all roads lead to this carrying capacity. If we're less than that, we can grow towards it. If you ever exceed it, you're going to decrease towards it. Okay? All right, so that's kind of the big idea in terms of understanding what logistic growth is, how the carrying capacity, population tie into each other. That's kind of the big thoughts. So now in terms of problems, yesterday, let me just do this. So again, yesterday when I gave you this differential equation, and you'll still want to know this, we did it a few times, and then ultimately we talked how like this is our velocity. If we now want our position, we don't have to do the work all the time. We just know that when we integrate this particular differential equation, it always resulted in the exponential growth and decay formula from last year. Okay? This is for rates of change. This is for our population. So now something similar needs to happen with this. Because if this is our rate of change, if I now actually ask you what is our population at a particular time, wouldn't we need to integrate this to come up with our population equation? All right? So that's what this mess you're going to look at next is. So yesterday, we did 2 or 3 of these in a row, and then we just talked about why would we do all the work when every single time we know it's this. But those steps here is like 3 steps, so you could, and it's not awful. This one here, you can look, there's about 15 steps here, okay? So here's this process, and I have it all written down, so I'll just kind of make some notes, make sure we can kind of follow along where all of the stuff is coming from. So this is the new differential equation. This is our logistic growth differential equation. Again, it starts out exponential. All right, that's what I have highlighted in blue. That is yesterday. But then this idea of carrying capacity, leveling off, that's why we introduced the parentheses part. Okay? So we're just going to clean this up. Ultimately, what we want to try and figure out is what does the population equation look like once we integrate it? So it's going to be a similar process to yesterday. You're going to take all the p's, we're going to divide those over, and then the dt you're going to multiply over. So that's why the dt is now over here, and then this got divided over. Then all I did in the next step, this 1, since we want this to have a common denominator, I wrote the 1 as like a k divided by a k, because once I have a common denominator, we can come up with this denominator here. And then whenever we divide by, well, then I threw integrals in front, so nothing really changes from here to here. But from this step to this step, when we divide by a fraction, isn't it the same as multiplying by the reciprocal? So I'm dividing by this fraction. If we multiply by the reciprocal, we're now going to get this. Okay? Now, there is a step I didn't show here because I like to show it and explain why this exists in this chapter. So from this step to this step, there's no work for this. We're going to show why this ended up like that. And the reason it is in this chapter, take this fraction here, so go ahead and do this work off to the right. This you will want to see. See how you have 2 different factors in your denominator? The reason this model is taught in this section is because this is a partial fractions idea. So this is one of the ones where we're going to take our k, and then we're going to do, and then the p over k minus p, and we're going to set that to a over one of the factors, and I'm going to make that the p, and then our b over the other factor, which is this k minus p. Because we're trying to integrate the left side, so if I can break it down into the partial fractions and know what a and b are, then we can go ahead and do that. So this is our whole process here where we're going to do the k is good on the left. A has to get multiplied by the k minus a p. So we're going to just distribute here. So you get ak minus ap. The b has to get multiplied by the p. So we're going to do b times p. And then we group these together. So we have this ak. I'm going to pull out the p. So we'll get a negative a plus b is the coefficient of your p. And this is a nice one because right away the coefficient of k over here is a. The coefficient of k over here is just a 1. So what does a have to be? 1. So very quickly, we now know a is a 1. And then if we go to this guy, a negative a plus b, write this, the negative a plus b, what was the coefficient of p on the other side? 0. So if we now know our a is a 1, so negative 1 plus b, then our b would also then have to be a 1. All right, and then that is where this step comes from. All right. All right, then next step should be nice. So if you look at this guy, the antiderivative of 1 over p is the natural log of p. The antiderivative of 1 over k minus p is the natural log of k minus p. And then again, keep this straight for Friday. I promise you people are going to miss this, so don't be one of those people. Because this had a negative in front of it, we had to divide by a negative. So that's why you're going to get the minus sign there. Okay? Then, because you're subtracting natural logs, we can write it as 1 natural log. Right? So all we did is use our natural log properties to get this. And then we used e to get rid of this natural log, giving us this. Then, do not flip this, because this step here is important. This is going to yield another thing. Make sure I put this down right, that you're going to want to know. All right, so in this step here, off to the right, there's 3 formulas you're going to want to memorize. This is going to give you the second one here in a second. All right, so when you look at this guy here, what I'm going to have you do, if I flip this around, so go ahead and flip that and put k minus p over p. So we agree just did the reciprocal. So if I now go to the other side, I would want to do the reciprocal of this side as well. So what that would initially look like is 1 over c e to a negative k, or sorry, e to the kt, right? We just did the reciprocal of it. So we just flipped everything. But can't I move this guy back up? And if I do move it back up, wouldn't it now just be c e to a negative kt? Then, if we eventually, which we're going to do in a moment, talk about at the time of 0, we're going to let our population variable, p, be our population at that particular time. We're going to use that little initial condition to find what c is. So if I now ask you what c is, go ahead and plug in. You're going to get c equals e to the 0. We're going to let our time be a 0. And at the time of 0, our population is p sub 0. All right, this is going to play a big role in a moment, so go ahead and box that up, and we're going to revisit that momentarily. All right. Okay, so on the next page, we're continuing in our goal. Just again, don't lose sight of our goal. We're trying to get p by itself. What does p equal? So now we have 2 p's. So I'm going to divide the p over. So that's where this guy went. That's where this comes from. Then I did p divided by p to get this 1. Because now, we're trying to solve for p. So then I'm going to add the 1 over. So that's where this comes from. And then if I multiplied both sides by p, and then take this expression, divide it over, we get this. And then the thing that you just boxed, remember how we talked about 1 over c e to a negative kt? I can rewrite this, so I'll do it here initially, as c e to a negative kt plus a 1. All right, that was from the front. So this is what we get. And then in this formula, our general c is this variable a. Okay, so a and c are largely equivalent to each other. So after all that, and again, you don't necessarily have to reproduce that. We don't want to have to reproduce that. Here is the big ta-da moment. Finally, after all that, this is our population logistic differential equation. Okay, so the big takeaway, what you're going to want to know really, really well, is the differential equation for logistic growth was the guy from the front page. And then the population equation, because we do not want to go through all of that work again, is this. Oops. Because whenever we see this, unless you want to go through those 15 steps that we just went through, we want to know that if I actually ask you a population equation, we can jump right directly to this. Okay? In terms of what your variables are now, this is your carrying capacity. This is your time. The little k is still your rate. And then this A is our unknown constant. But what we did on that front page, what we found that unknown constant to always equal on the previous page at the bottom was this. All right, so now, understand the first page really well, why this differential equation was useful. And then the next thing, get these three things memorized. That differential equation, population equation, and then how we can figure out what the variable A is equivalent to. And if we can get those three things down, then the problems themselves are pretty easy. All right? Okay, so now go to these problems. So number 2 says, write the solution of the initial value problem given by this. So what this is your differential equation. The initial population was 100. So what this is ultimately asking you to do, when we solve an initial value problem, we want to find the initial function. So this is really just asking you now to convert. I am giving you this guy, and based upon what that looks like, you're going to go into this. And again, we do not want to go through, to make this happen, we do not want to go through all of these steps to make that happen. Okay? So what we want to be able to do is know that the population equation, let me write the general one first that we just worked through and found, is this. And we should be able to convert back and forth. Okay, so don't flip. See if you remember this from the front page. I'm going to erase the capital K in the numerator because I should be able to look at the differential equation, and the capital K is what value based upon this. And the capital K is our carrying capacity. What would that be? The 1,000. So you're going to put 1,000 in the numerator. All right, I'm going to erase the little k because I should be able to look at this differential equation and look at that and know that my little k is what? 0.08. So you're going to plug in 0.08 right here. Now, the A we need, but again, A isn't just one particular thing. A is the third equation that you now need to get down pat. You need to do a little work to find that. Your A should be the carrying capacity. And again, what's our carrying capacity? 1,000. Minus the initial population. So that's why you had this here. At the time of 0, your initial population was 100. And then divided by the initial population, which was 100. So in this model, with this information, our carrying capacity ends up being 9. So I'm going to revisit the A here. I'm going to replace it with a 9. Okay, got that? All right, then definitely need calculators. These are a little ugly to plug in, so definitely have calculators plug these in. Now we can answer the first 2 questions. All I want you to do in part A is find the population after 40 whatever, or years, days, months, whatever the units would have been for this particular problem. So you now have this equation. This is our population equation, and you're just plugging in 40 for that. Okay, so do that. And let me see here. Okay, and we'll in here, it doesn't say it, but whatever their population is, we probably don't have half people. All right, also, if we understand this model, this number should fall in between what 2 numbers? Your answer should be between what 2 numbers? Julia? Good. 100 is your initial population. Our carrying capacity is 8,000, so our population should fall within that window. Okay? All right, and it does. It should be 732. Are we getting that? If we round to the nearest whole number? Okay. So that population would be 732. And again, A or B is the same idea, but the reason I'm doing this more than anything is understand the big picture and the model that we're dealing with right now. The population at 80 should now fall between what two numbers? Good. It better fall between 732 and your carrying capacity again of 1,000. Okay? All right, and then plug it. You can just pull up your old one and put the 80 in for the 40. Save some time here. And then that should give us to the whole number 985. Okay? Okay, then part C. Part C was here. Find the time the population reaches 900. So this is our population equation, right? So now all this is really asking us to do is to find when the population itself, the left-hand side, was 900. So we're going to let our population be 900. Set it equal to that right-hand side, where the only variable on the right-hand side is a time variable. Oops, I forgot the 8. But then now, a little ugly, so we now got to go through, work, and solve that equation. All right, I'm going to treat it as just a proportion. I'm going to cross multiply those guys. So I'm going to get 9e to the negative 0.08t plus 1. The 900 would have gotten divided over, so that's 10/9. Subtract the 1 over. So that would be 10/9 minus 9/9. So now that's 1/9. Divide by 9. So 1 over 81. Use your natural log to get rid of the e. So then we get the natural log of 1 over 81. So then final answer should be the natural log of 1 over 81 divided by a negative 0.08. You can see all that. All right, so what does that give us? All right, it should give us, this we can have decimals, we can have partial units of time. So we'll go to our 3 decimals. Check that on me too, make sure we get that. Okay. Okay, y'all get that? Okay, and then real quick, go to that third example. Suppose the population grows according to the logistic model, so that puts into play everything that we did here in the last half hour, with the carrying capacity of 6,000 and a little k of 0.0015 per year. I want you to write the logistic differential equation. So that is the first one from the front page. Here is what it looks like without any details. But now take these two pieces of information. This is your carrying capacity. This as your little k. You're just plugging it in. And that's all we're doing for part A. Just to make sure we can take that data, use the new little equation here. All right, and again, the 6,000 is which of the k's? The lower, the bigger one, right? The one that's on the bottom. So this is 6,000, and then the little k is your rate. This is 0.0015. I can squeeze that in there. All right, and then do B. If the initial population was 8,000, now do the second formula that we need to get memorized. Write the formula for your population based upon that differential equation. is this really, oops, don't do that. Can we look at this differential equation and translate it into our position equation without separating the variables and going through all the nonsense we had to do in the middle of this set of notes? So our numerator, the big K here, should be what? Was it? So what's our numerator? 6,000. The little k, that's then has to be the other one, the negative 0.0015. And then the third thing then is the A. You have to know then that the A, this is the third big thing, if you walk out of here knowing these three, you're in pretty good shape, is the carrying capacity minus the initial, which I told you was 1,000. And we do that, our A ends up being what? Oops, 5. So you plug in the 5. And then now, we don't have time, but now that you have that, couldn't you find your population after 50 years? Plug in the 50, whatever that spits out will be your population at that time. Okay? Some of you are probably already there. That was like 1,064, I think, all right, if you did that. All right? Okay, let me see.